In this video, I'll go through some matrix representations of reflections and rotations in R2. So first, let's look at the matrix A, 1, 0, 0, minus 1, and multiply that by a vector in R2. And what do we get? So for the x-coordinate, we're going to get x again. And for the y-coordinate, we'll get minus y. So in terms of the point x, y, we are getting reflected across the x-axis to x minus y, which is going to be down here. So that's the effect of this transformation. We are reflecting in the x-axis. Sometimes you'll see this written as reflecting in the line y equals 0, because all along the x-axis the value of y is 0. Okay, next let's look at matrix B, minus 1, 0, 0, 1. Multiply that by a vector in R2, and what do we get? So this time we get minus x for the x-coordinate and y for the y-coordinate. So in this case, on the diagram, that point xy is going to go to minus xy, so that's going to be over here, and so this is a reflection in the y-axis. So we are reflecting in the y-axis, also described as reflecting in the line x equals 0. Next, let's look at matrix C, 0, minus 1, 1, 0. What happens if we multiply that by a vector in R2? So now we're going to have minus y for the x-coordinate, and we're going to have x for the y-coordinate. So what happens in the diagram? So if we think of, maybe I'll use some colors here. So this point xy is x in the x direction, and maybe I'll use a different color. Let's use green. And then this is in the y direction. So we're going minus y in the x direction for the transformed point. So that's the green line. So we're going as far as this in the x direction, and we're going x units in the y direction. So that's going to be the red line. So we're going to be up here. So we'll be at the intersection of the green and the red line. So we're going to be, let's go back to blue, we're going to be here. Okay, so the point that started at xy has been transformed to the point that ends up at minus yx. And so what's happened is, if I just draw this diagonal here and this diagonal here, the point has been rotated 90 degrees in the counterclockwise direction. So this matrix C represents a rotation of 90 degrees counterclockwise about the origin. Okay, let's look at matrix D now. You can probably guess what this one is. 0, 1, minus 1, 0. See what happens to the point xy. It's going to go to y minus x. Okay, so if I use my red and green again, let's think about this. So the red going to be the shorter part. The green is going to be the longer part. If I draw a rectangle, and we are going to y in the x direction, so y in the x direction will be, let's see, y in the x direction, so that'll be here, and then minus x in the y direction, so that'll be down here. So we're ending up at this point here, and so if I draw the diagonals on those rectangles like this, so we've rotated this way about the origin by 90 degrees. Okay, so let's write that down. So this matrix D represents a rotation of 90 degrees clockwise. What about a rotation of theta degrees? So theta can be anything now. So let's go to this diagram down here in the corner. So let's think about the vectors 1, 0 and 0, 1 and see where they end up after rotating by theta degrees. So here's E1, the point 1, 0, and if I rotate around this circle of radius 1 about around the origin and I go theta degrees, I'll end up here. And then point E2 is up here, 0, 1. I'm going to rotate by theta degrees around the origin and it's going to go around the circle over here. Okay, so let's figure out the coordinates of those ending points for rotating by theta degrees. So this point and this point. So let's start with this point. So if I've gone theta degrees, the x coordinate is going to be the length of this part of this triangle. And in terms of theta, that's going to be cosine of theta, because it's adjacent to the angle. So let's write that in. So we're going to have cosine of theta for the x coordinate. And then what about the y coordinate? So that's going to be this side of the triangle. So that's opposite the angle. So that's going to be the sine of theta for the y coordinate. And then let's do the same thing for E2. So 0, 1, where's that going to go? So the x coordinate now is this blue dashed line. That's opposite the angle, so that's going to be the sine of theta, but it's in the negative direction. So this is minus sine theta. And in the y direction, it's going to be this side of the triangle, and that's adjacent to the angle theta, so that's going to be the cosine of theta, and it's in the positive direction. So cosine of theta. Okay, so if we put all that together in terms of a matrix, so we'll put the first column is going to be what happens to E1, 1, 0, so that goes to cosine theta, sine theta, and then the second column will be what happens to E2, that goes to minus sine theta, cosine of theta. And this matrix represents a rotation of theta degrees, and the convention is this that rotations are positive, rotations are counterclockwise, as we've drawn it in the diagram there. Okay, and we could just test that out for one of our earlier examples. If theta is 90 degrees, then cosine of theta is 0, so we'll have zeros here, and sine of theta is 1, and so we'll have -1 here and 1 here, and that matches our matrix C up here.